Stars are just giant balls of burning gas, right? Wrong. What the heck is actually going on up there? Stars are massive spheres of plasma held together by their own gravity. They're basically nuclear fusion reactors floating in space, converting hydrogen into helium and releasing enormous amounts of energy in the process. But where do they come from? Well, space isn't actually empty. Between stars, there are massive clouds of gas and dust called nebulae, mostly made of hydrogen and helium left over from the Big Bang. These nebulae are stellar nurseries. When a region of the cloud gets dense enough, maybe from a shock wave from a nearby supernova or just random turbulence, gravity takes over and the cloud starts to collapse. As it collapses, it spins faster, kind of like an ice skater pulling in their arms, and forms a disk. The center gets denser and hotter, creating a protostar, which is basically a baby star that isn't quite hot enough to fuse hydrogen yet. When the core temperature hits about 10 million Kelvin, hydrogen atoms start slamming into each other with enough force to overcome their electromagnetic repulsion and fuse together. Boom! Nuclear fusion begins and a star is born. This is called the main sequence, and it's where stars spend most of their lives, just chilling and fusing hydrogen into helium. The energy released from fusion creates outward pressure that perfectly balances the inward pull of gravity, keeping the star stable. How long a star stays on the main sequence depends entirely on its mass. Massive stars burn through their fuel incredibly quickly, lasting only a few million years. Smaller stars like red dwarfs can last trillions of years. Our Sun? About 10 billion years total, and we're halfway through. Stars come in different sizes, and mass determines everything about their fate. You've got red dwarfs, which are the smallest and coolest, then yellow dwarfs like our Sun, then massive blue giants that are dozens of times more massive and burn way hotter. The more massive a star, the hotter and brighter it burns, but paradoxically, the shorter it lives. A star 10 times the mass of the Sun only lives about 20 million years, while a red dwarf can burn for trillions. So what happens when a star runs out of hydrogen? Well, for stars like the Sun, things get interesting. The core contracts and heats up, while the outer layers expand massively, turning the star into a red giant. The core gets hot enough to start fusing helium into carbon and oxygen. Meanwhile, the outer layers expand so much they can swallow inner planets. In about 5 billion years, the Sun will engulf Mercury, Venus, and possibly Earth. But this helium fusion doesn't last long, maybe 100 million years. When the helium runs out, the core contracts again. But for stars like the Sun, it never gets hot enough to fuse carbon. Game over. The outer layers drift off into space, creating a planetary nebula, which has nothing to do with planets. It's just called that because early astronomers thought they looked like planets through their telescopes. What's left behind is the hot, dense core, now called a white dwarf. It's about the size of Earth but contains about half the mass of the Sun. A teaspoon of white dwarf material would weigh about 5 tons. White dwarfs don't fuse anything anymore. They just sit there, slowly cooling down over billions of years, eventually becoming black dwarfs, which are theoretical because the universe isn't old enough for any to exist yet. But massive stars? They go out with a bang, literally. When a star is at least 8 times more massive than the Sun, it has enough gravity to keep the fusion party going. After hydrogen and helium, it starts fusing carbon, then neon, then oxygen, then silicon, building heavier and heavier elements in layers like an onion, with iron at the very center. Here's the problem. Fusing elements lighter than iron releases energy, but fusing iron actually requires energy. So when the core turns to iron, fusion stops dead. No outward pressure means gravity wins. The core collapses in less than a second, going from the size of Earth to about 20 kilometers across. The outer layers come crashing down and bounce off the incredibly dense core in one of the most violent events in the universe, a supernova. A single supernova can briefly outshine an entire galaxy of billions of stars. The shockwave tears the star apart, blasting heavy elements into space. Everything heavier than iron, including the gold in your jewelry, was formed in supernova explosions. But what happens to the core depends on how massive the original star was. If the core is between about 1.4 and 3 solar masses, electron degeneracy pressure can't hold it up anymore, so it collapses into something even weirder. Protons and electrons get crushed together to form neutrons, creating a neutron star. These things are insane. They're only about 20 kilometers across, but contain more mass than the sun. They're so dense that a sugar cube of neutron star material would weigh about 100 million tons. The gravity is so intense that if you dropped an object from 1 meter above the surface, it would hit at about 7 million kilometers per hour. Some neutron stars spin hundreds of times per second and shoot out beams of radiation from their magnetic poles. If those beams sweep past Earth, we see pulses of light, which is why they're called pulsars. But if the core is more than about 3 solar masses, not even neutron degeneracy pressure can stop the collapse. The core keeps collapsing past any known limit until it becomes a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from inside the event horizon. The matter collapses down to a singularity, a point of infinite density, where our understanding of physics breaks down completely. Black holes warp space-time so severely that time itself slows down near the event horizon. If you watched someone fall into a black hole, you'd see them slow down and freeze at the edge, even though, from their perspective, they'd fall right through. And yes, they would get spaghettified. The difference in gravitational pull between their head and feet would stretch them into a long, thin strand. Fun times. So we've got 3 possible endpoints: white dwarfs for low-mass stars, neutron stars for medium-high mass stars, and black holes for the most massive stars. But the story doesn't end there. All those heavy elements created in stars and supernovae get scattered into space, enriching the interstellar medium. New stars form from these enriched clouds, bringing planets with them that have all the elements needed for life. We are literally made of star stuff. Every atom in your body, heavier than hydrogen, was forged in the core of a star or in a supernova explosion billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all came from dying stars. Now, things get even more interesting when stars aren't alone. About half of all stars exist in binary or multiple star systems orbiting each other. This can lead to some wild interactions. If a white dwarf is in a binary system with a normal star, it can steal matter from its companion. If it accumulates enough mass to exceed 1.4 solar masses, called the Chandrasekhar limit, it can't support itself anymore and collapses, triggering a Type 1a supernova. These supernovae are special because they always release the same amount of energy, making them standard candles that astronomers use to measure cosmic distances. This is actually how we discovered that the universe's expansion is accelerating. Neutron stars in binary systems can also steal matter from a companion. And when two neutron stars spiral into each other and merge, they create a kilonova, which produces gravitational waves and synthesizes elements even heavier than iron, like platinum and uranium. Some stars aren't stable during their lives. Variable stars change in brightness over time due to internal processes. Cepheid variables, for example, pulsate regularly, expanding and contracting with their period directly related to their luminosity. This period luminosity relationship makes cepheids incredibly useful as cosmic distance markers. By measuring how long they take to pulsate, astronomers can figure out how bright they actually are, compare that to how bright they appear, and calculate their distance. There are even weirder objects out there. Magnetaires are neutron stars with magnetic fields a quadrillion times stronger than Earth's, powerful enough to disrupt atoms at a distance. Quark stars might exist in between neutron stars and black holes, where matter breaks down into quarks. Hypothetical strange stars could be made of strange quark matter, which might be more stable than normal matter. There are also zombie stars. Sometimes, in a Type 1a supernova, the white dwarf doesn't completely explode. Part of it survives, creating a remnant that's partially burned but still hanging on. Spooky. Astronomers classify stars into populations based on their age and composition. Population 1 stars, like the Sun, are young and metal-rich, formed from gas enriched by previous generations of stars. Population 2 stars are older and metal-poor, formed earlier in the universe when there were fewer heavy elements around. Population 3 stars are theoretical, the very first stars ever, made of only hydrogen and helium, and no confirmed ones have been found yet. So, what's the long-term future? Well, star formation requires hydrogen, and while there's still plenty in the universe, it's not infinite. In about 100 trillion years, the last stars will burn out, and the universe will go dark. Eventually, even white dwarfs and neutron stars will cool completely. Black holes will slowly evaporate through Hawking radiation, though this takes an incomprehensibly long time, like 10 to the power of 100 years for a solar mass black hole. In the far, far future, the universe might consist only of black holes, dead stellar remnants, and elementary particles, slowly drifting apart in an ever-expanding, ever-cooling cosmos. Pretty depressing, but that's trillions of years away, so don't worry about it. Understanding stellar evolution isn't just cool trivia. It explains where the elements come from, how galaxies evolve, and provides the physics needed to understand the universe's structure and fate. It also helps us search for life. Knowing which stars are stable enough to host habitable planets, which ones produce the right elements, and how long they'll last gives us insight into where to look for alien civilizations. Stars are the engines that drive cosmic evolution, the furnaces that create the building blocks of everything, and the markers we use to map the universe. Pretty impressive for giant balls of plasma. And that's how stars are born and die, from cosmic dust to white dwarfs, neutron stars, and black holes. The universe is pretty wild.